Hi everyone! Today we're going to talk about how to describe the transformations of a function algebraically. To complete this problem, we'll first identify the transformations we need to describe, and then show algebraically how each of these transformations will affect our original function. Let's take a look. In this particular problem, we've been given the function, or the theoretical function, y equals f of x, and asked to algebraically describe the following transformations of y equals f of x. So what they're basically saying here is that we haven't been given f of x explicitly. It could be anything. It could be x plus 7, it could be x cubed plus x squared minus 4, it could be any function, but they're saying given any function, perform the following transformations and indicate what that transformation would look like in conjunction here with f of x. So this will be just a great overview for how to perform the following transformations and should give you a better idea of how to look for transformations when you see them. So given y equals f of x, if we want to shift that graph, remember no matter what it is, but we want to shift it up 3 units, then our function would be y equals f of x plus 3. And that's easy to understand because no matter what we plug in for x here, the resulting y value would be 3 units more if we just add 3. So it would be a vertical shift up 3. And the same will go for shifting down 3. We'll just get y equals f of x minus 3. This would shift the graph down vertically 3 units. When we're talking about shifting left and right, we have a similar concept except that this plus 3 and negative 3 here needs to be included in the function. So instead of having it be separate, right, here we've kind of just separately added on a plus 3 and separately added on a negative 3. But in this case, if we want to shift right 3 units, then our function will be y equals f of x minus 3. So instead of just adding 3 or subtracting 3 separate from and outside of this f of x function, it's integrated inside of the function, which means that if our original function were, let's say, x cubed, and we wanted to shift it right 3 units, we would have to plug in x minus 3 for x, and we get the quantity x minus 3 cubed. So we really have to incorporate that negative 3. And it's somewhat counterintuitive that it's a minus 3 when we're shifting to the right, but it is opposite like that from what you would think. It's minus 3 here. Shifting left 3 units is y equals f of x plus 3. So again, and maybe we can go through and do this here, if we had a function y equals, let's say, x squared, right? Then our transformation here to shift up 3 would just be x squared plus 3. To shift down 3 would be x squared minus 3. To shift to the right would be y equals x minus 3 squared. And to shift to the left would be y equals the quantity x plus 3 squared. So you can see the difference there. If we're going to reflect about the x-axis, that means we're going to flip it over the x-axis exactly where it is, we'll get y equals negative f of x. So we just add that negative out in front of the f of x or multiply by negative 1. If we want to reflect about the y-axis, we have to incorporate that negative inside of our f of x and we'll get f of negative x. So that's the difference here, and the transformation looks like this. Again, if we have the function y squared, then we would get y equals x squared. We would get y equals negative x squared to flip it over the x-axis. We would get y equals negative x squared to flip it over the y-axis. And finally, if we want to stretch vertically by a factor of 3 or shrink vertically by a factor of 3, then our functions look like this. To stretch vertically, we want to say y equals 3 times f of x. That means every y coordinate on our original function, x squared, will now be 3 times what it was in the original function. If we shrink vertically, we want to say y equals 1/3 f of x. And every y coordinate that was on our original graph will now be 1/3 what it was originally. What that looks like here, of course, is y equals 3x squared and y equals 1/3 x squared. And we won't take the time to do it here, but if you started with the function x squared and you graphed all of these transformations, you would see visually how the graph would get shifted up 3 units, down 3 units, to the right, to the left, etc. And that's it. That's just a basic overview of transformations of functions up, down, right, left, and flipping over the x and y axis and stretching and shrinking. So I hope you found that video helpful. If you did, like this video down below and subscribe to be notified of future videos. Hi everyone! Today we're going to talk about how to graph transformations of a function. To complete this problem, we'll first graph the original function and then separately consider each of the transformations. Let's take a look. In this particular problem, we've been asked to graph various transformations of the function y equals the square root of x. We're going to be looking here at 4 basic transformations, but remember that there are many types of transformations. The purpose of graphing these 4 in particular is to start getting you comfortable with transformations, but remember that if you ever run into transformations on a test, you can always just plug in points for x and then start plotting your results on your axes. That's your fail-safe when it comes to transformations. And what we're going to talk about today should really just familiarize you with the basics so that you can get these done as quickly as possible. I've graphed our original function, y equals the square root of x, on this first set of axes. Over here on the second set of axes, we're going to be graphing the transformation y equals the square root of x minus 2, this function right here. What you want to realize is that you can completely separate the constant, negative 2, from the square root of x. That's in contrast with, for example, this function down here where you have 2 times the square root of x. You can't completely separate them because they're multiplied together, but when you have 2 terms like this, the square root of x and a constant, negative 2, that are added or subtracted from one another, you can think about being able to separate them. And when the only thing that's transforming your function is a constant like this, that means you're dealing with a vertical transformation and your function's just going to be moving up or down within the same set of x values. So what we mean by that is that we have the function y equals square root of x minus 2. Every point that would be on our original graph, y equals the square root of x, is just going to get moved down 2 units. So in other words, we're going to take every point and shift it down by negative 2. So that means that, let's say it's about here, we'll take every point and shift it down by negative 2 so that our transformation actually looks like that. In this third example here where we have y equals negative square root of x, we have, notice, a negative 1 multiplied by our square root of x term. Whenever you have a constant multiplied by your original function, that means you're either going to be stretching or shrinking your graph and or flipping the graph across an axis. In this case, every point you plug in for x is going to return a certain y value. But this time, now that we've multiplied by this negative out in front, we're going to get the same y value but multiplied by negative 1. So this is just a transformation flipped across the x-axis and the graph looks like this. So just remember that if you've got your original function, square root of x, with a negative out in front, that means you're going to be flipping it over the x-axis. Similarly here with our next function, y equals 2 times the square root of x, we've got a constant coefficient multiplied by our original function. Same with the last one, we had negative 1 multiplied by our original function. Now we have 2 multiplied by our original function. And what that means is that we're going to be stretching the graph by a factor of 2. So when we draw the graph, instead of every y-coordinate lying along the original function, the new y-coordinate we get will be double what the old one was. So that'll look something roughly like this. And the way you can think about it is we would have had our original y-coordinate here. Let's say that that's at 1. Well, our new y-coordinate will be double that, a factor of 2. So the new y-coordinate will be here at 2. Same thing here, if our y-coordinate was 3, our new y-coordinate is 6. So it just stretches the graph by a factor of 2. Think about it this way. If we had had negative 2, if we had had y equals negative 2 times the square root of x, we would have been stretching the graph a factor of negative 2 and flipping it across the x-axis, and that would have looked like this. Keep in mind that the same thing goes for shrinking the graph. If we had the function y equals 1/2 square root of x, we're dividing our original function by 2 instead of multiplying it by 2, and that would have looked something like this. So I hope that gives you an idea of the transformations you'll see when you have a constant coefficient multiplied by your original function. In the last graph, we have y equals the square root of negative x. And this one here is similar to this graph that we did in the sense that all we've done is add a negative sign, except that here we've added it in a different place. It's inside our square root sign instead of outside our square root sign. Remember that before, the negative outside of the square root sign meant that we were flipping across the x-axis. Since we have a negative inside our square root sign, that means we're going to be flipping across the y-axis. So our graph is going to look like this. And that makes sense because when we have a negative sign inside our square root here, we know right off the bat that we can only have a positive value underneath our square root. In order to get a positive value underneath the square root, that means we're going to need to put in a negative value for x, so that, for example, if we plug in a -2, we'll get the square root of -2, which will equal the square root of +2. The only way to get a positive value underneath the square root sign is to insert a negative value for x, which means that our domain for this function can only be negative numbers, and that's why we see the function getting flipped across the y-axis like this. The domain of our new function is only negative numbers. And that's it. That's a preview into some basic transformations. So I hope you found that video helpful. If you did, like this video down below and subscribe to be notified of future videos. Hi everyone! Today we're going to talk about how to use transformations to sketch the graph of a function. To complete this problem, we'll first sketch a small piece of our function, then modify it one transformation at a time until it represents the complete function. Let's take a look. In this particular problem, we've been asked to use our knowledge of transformations to sketch the graph of y equals 1/2 e to the negative x minus 1. And all I want to show you here is that you can sketch the graph of a function that you know, and then use your knowledge of transformations to build out the rest of your function. So what I mean by that is we could, for example, recognize that we have e to the x. This function here, or this part of our function, e to the negative x, is just e to the x, but with a negative x substituted in. So what we could do is we could start with the graph of e to the x, and if we know what that looks like, it's a common function, it might be a graph that we know, we can start with that, and then we can change e to the x into e to the negative x, and then we can apply the 1/2, and then we can apply the -1. So here's what that could look like. We could sketch the graph of e to the x, and that looks something roughly like this. You may know that it's a curve that looks like this. It intersects the y-axis at y equals 1, and this would be e to the x. But we don't have e to the x, we have e to the negative x. So what we want to do is recognize that all we've done here, right, this function is f of x equals e to the x. Well, we've gone ahead and said f of negative x because we're plugging in negative x for x. Well, what we should know from our knowledge of transformations, or our study of transformations, is that if you plug in negative x for x into a function, it's just going to flip the graph across the y-axis. So we're going to have the same function, except that it's going to be backwards like this, flipped across the y-axis. So again, we'll intersect the y-axis at y equals 1, and the graph is just flipped across the y-axis like this. So now we have the graph of e to the negative x. Well, our next step is to apply this 1/2 here, right? We need 1/2 times e to the negative x. So what we want to do in that case is say this is going to be the graph of f of x equals 1/2 e to the negative x. And we know from transformations that multiplying by 1/2 means that we're going to shrink the graph vertically by a factor of 2. So instead of the graph intersecting the y-axis at 1, it needs to intersect at 1/2, and every y-coordinate will be half what it is. So if this y-coordinate here, for example, were 4, our new y-coordinate here will be 2, y equals 2. So we just shrink by a factor of 2. So I may not draw this perfectly, but maybe what that looks like would be something like this. We'd intersect at 1/2, we know that, and we would have every y coordinate be half of what it used to be, and that would be 1/2 e to the negative x. And then our final step would be to apply this -1 here. We know from studying transformations that adding a -1 like that is just going to shift our graph down 1 unit. So if we're talking about f of x equals 1/2 e to the negative x minus 1, we have the same graph that we did over here, except we move it down 1 unit. So instead of intersecting the y-axis here at 1/2, we're going to be intersecting at -1/2. So that'll look something roughly like, we call this -1/2 here, something roughly like this maybe, -1/2 here, and that would be the curve like that. So it's a little rough, but you get the idea. So as you can see, we started with e to the x, and we just manipulated that one step at a time using what we already know about transformations to sketch the final graph of y equals 1/2 e to the negative x minus 1. So I hope you found that video helpful. If you did, like this video down below and subscribe to be notified of future videos.